Alright, this is section 15.5. This is on surface integrals of functions. So this is the second to last new integral we'll learn in the course. And so for an intro, I'm going to do this a little bit differently than the other ones. What I'm going to do is I'm going to sort of give a situation, give sort of a loose calculus interpretation of what's going on, and talk about what we might be trying to measure. That may sound a little abstract, that's okay. Then we'll bring up some notation and then a method of evaluation. So this is the way to approach it. So suppose that sigma is a surface in 3D space. All right, like a sphere or cylinder or a paraboloid. So suppose that f as a function, f of x, y, z, is defined at every point on sigma. So for every point on sigma, you can plug that point into f and you get a value out. This is defined at each point on sigma. So examples of this might be like a density function, for example. So, but let's approach this a little bit differently. Suppose then we take sigma and we're going to chop it into little rectangles, approximately. Into small rectangles. So I say approximately because if sigma is curved, you can't chop it into actual rectangles, but you can approximate it by rectangles. So for example, if you had something like a paraboloid, you could chop it into small rectangular pieces. And again, like we're thinking of this really informally. Don't worry if the rectangles don't match up. Just think, hey, we're gonna chop it up into pieces like this. And then what we'll do is for each piece, for each rectangle in this new picture, pick a point on the rectangle, plug it into f, and multiply that value by the area of the rectangle. And then what we'll do is add all the resulting values up. So we'll say add resulting values. So abstractly what's going on is we could say that is take the sum over all rectangles of the quantity f at a point in the rectangle multiplied by the area of the rectangle. Then what we'll do is make the rectangle smaller and smaller and take the limit of this result. So we'll take the limit of this as the size of the rectangles heads towards 0. So the result will denote this way. We're going to denote the result by the integral of f. It's really, let's be clear, it's the surface integral over sigma of f. And this is denoted by it's a double integral over sigma of f of x, y, z d capital S. So we had a lowercase s in an earlier integral, in the line integral of a function. This is a capital S. So what could this give us? So I'll give you two possible examples. if the function is 1, think about what happens. We take f at a point in the rectangle, that gives us 1. We multiply it by the area of the rectangle, that gives us the area of the rectangle. And then we make the limit as the size of the rectangles go to 0. So we have smaller and smaller rectangles, but more of them. And the eventual result is the surface area of sigma. So if f is 1, then this guy, ds, this is the surface area of sigma. And the second example, otherwise, you could think of, like, for example, if f is density, say mass density. Then if we integrate this function, integrate f, we get the total mass of sigma. And this doesn't have to be mass density. It could be, for example, electrical charge density is another good one. But when you find this integral, what you're doing is you're finding the total of that quantity over the entire region. So if that's the case, how do we evaluate this thing? So luckily, just like when we did line integrals of functions had just one way to do them for us. Same thing for surface integrals of functions. There's a single way to do them. So 2, method of evaluation. So for us, there is one way to do these guys. So this is as follows. So, just like when we did the line integral of a function, what we did for that particular case is we parameterize the curve. So here we're going to parameterize sigma. And we're going to do this just like in section 14.9. I'm going to do a little more complicated examples here, but that's the spirit of the problem, right? So we parameterize sigma. This is C section 14.9 by, remember this was with an R of U and V. And so this will have an X component, like an I component, X of UV, I, J component, Y of UV, J, and a K component, Z of UV, K. This is with U and V restricted. So I'm going to say this might be a bit confusing, even though we've done this before. Restricted by a region R in the UV plane. So often inequalities. That's a bit confusing compared to 14.9 because I'm sort of tweaking it a bit because we know more now. That's all right. Let's just see how we go. So then what happens is the surface integral of f of xyz ds becomes the following. It becomes a double integral over R. Now, everywhere I see an x, I put x of uv from the parameterization. Everywhere I see y, y of uv. Everywhere we see z, z of uv. And then what we do is we multiply by the magnitude of the cross product of the partial derivatives of R. And this is dA. And then we do the result according to what R looks like. And I'm going to put a little note here, is that R is most often thought of as a set of inequalities, a pair of inequalities. And if the description of R is a bit confusing, that's okay for now. We're going to sort of hash through some examples, and I'll sort of draw some pictures of R as well as some sets of inequalities and pairs of inequalities, and we'll go through and we'll get to the point where we get an iterated integral, and then we can stop, because at that point we're simply just machines going through the process. So here's the first example. So what we'll do is this. We'll say, let sigma be the part of z equals, say, 25 minus x squared minus y squared. That's a paraboloid opening down with x between 0 and 2 and y between 0 and 1. So it's sort of like a rectangular piece of paraboloid. And let's say, let's find the integral over sigma of x, y plus z ds. So I'll draw a picture of this. The picture isn't really necessary to do this problem, but it can really help us see the parameterization. So here's sigma. So the paraboloid goes like this. This is the whole paraboloid. Sigma is a piece of this. And so sigma is the piece of this. I'm going to do sigma in green with x between 0 and 2. So just for reference, the x's and the y's both come out to 5 because this hits the xy plane at a circle of radius 5. So the sigma comes out to 2 in the x direction and 2 in the y direction. So it's like a patch of that paraboloid. So the way that we'll parameterize this is we'll do r, x and y are two good variables because they have nice inequalities. So we'll do xi, yj, and then z to be on the paraboloid needs to be 25 minus x squared minus y squared. Okay. And this is with x between 0 and 2 and y between 0 and 1. Now, these two things right here, those are describing our r, which if we drew them in the xy plane, this is not necessary for this, but it can be helpful, would be, let me do this in a different color, let me do this in red, because we've done that before. It's a bit small, but that's okay. That's the r right there. Again, the picture here isn't necessary, but it can maybe help. So then what we do is we say, okay, so now we need r sub x and r sub y, right? So if you look back at this expression right here, again, this won't be u and v. This will be with respect to whichever variables you've chosen, or that we've chosen for the problem. Use the variables we've chosen. So in our case, that's an x and a y. So then we'll do r sub x. That is 1i plus no j's minus 2xk. We'll do r sub y, which is no i's plus 1j minus 2yk. We'll cross those. So when we do the cross product, remember how this works? For the I component, I multiply 0 times negative 2y minus negative 2x times 1. So we get 2x I. When we do the j, we hide the j's. I do 1 times negative 2y, which is negative 2y minus 0, so that's plus 2y. And then for the k component, we hide the k's, and we do the little determinant. We get 1 times 1 minus 0 times 0, that's plus 1k. We take its magnitude. We get the square root of 4x squared plus 4y squared plus 1. So then what happens? I'm going to go back and I'm going to start this over here so we can fit it all in, because I like to keep everything on one page. The original integral that we're looking at, this is x plus y, xy plus z ds. This now becomes a double integral over r. Now, the x and the y's and the z's, I'm going to replace, in principle, by these three things right here. So I'm replacing x by x, which seems a little weird, but it's good to say it. So x becomes x, because it gets replaced by the I component of r. Y gets replaced by y. Z, however, gets replaced by 25 minus x squared minus y squared. Then we multiply by this new thing right here. This is pretty much like a Jacobian. Then we dA. And then to finish off, we just iterate according to r. So x goes between 0 and 2, y goes between 0 and 1. It doesn't matter which we do. Everybody's a constant. Put the same thing inside. In other words, same thing as above. dy dx. So I apologize, that's a little jammed in there. We'll spread the next example out. I'm going to clear the page and I'll do the next example. But again, look through it. They'll all be basically the same. We parameterized sigma. We had an r. We had restrictions on the variables that were in the r bar in the parameterization. Took the partial derivatives, took the cross product, took the magnitude. We wrote the surface integral as an integral over r, replaced x, y, and z by the I, j, k components, and then iterated accordingly. And then from here on out, you just evaluate. So take a second to look at that. I'm going to clear the screen and then work through another example. So second example. Now we have a lot more space. I can really clarify things here. So let's let sigma be the part of, we'll say, the cylinder x squared plus y squared equals 4 between z equals 1 and z equals 5. Let's find the integral over sigma of, say, xyz ds. So again, here's a picture of sigma. Picture isn't necessary as far as exams, for example, are concerned, but it can really help. So let me draw the sigma in green because we did that before. So all I'm doing right now is just drawing the sigma. I don't need to draw any other parts. Now keep in mind this surface is hollow because x squared plus y squared equals 4. Has a radius 2, and it extends down here from z equals 1 to up here z equals 5. And that's the cylinder, right? So we can parameterize this. So we need two good variables. So z is a good variable, theta is a good variable, so we'll use those two. We'll do 2 cosine theta I, 2 sine theta j, and zk. This is for theta between 0 and 2 pi, and z between 1 and 5. And if this is a bit confusing, take a look back at section 14.9, because we did a few things like this. This can really help. And again, these two inequalities are the r that we have. And a picture of this picture isn't really necessary at all. And maybe can be confusing. So if it's confusing, then just don't draw it. But if I had a theta z-axis, such a thing, theta would go up to 2 pi, z would go from 1 to 5, and the r that would be in play here would be this thing. Because really it's just a set of theta and z pairs that draw this surface. So then we proceed. We find r sub theta. So this is negative 2 sine theta I plus 2 cosine theta j plus 0k. We do r sub z. This is nice. This is 0i, 0j, 1k. Do the cross product. So if we hide the i's and take the determinant, we get 2 cosine theta. If we hide the j's, do the cross product, we get minus a minus here, so plus 2 sine theta j, and then 0k, because for the k's we get 0 minus 0. Take the magnitude, we get the square root of 4 cosine squared theta plus 4 sine squared theta. Sine squared plus cosine squared is 1. We get the square root of 4. This is 2. That's awfully nice. So then what happens? This is nice to have more space here. The integral over sigma of xyz ds. This becomes the integral over r. So now x and y and z, let me color code all this. The x gets replaced by the I component right there. The y is replaced by the j component right here. Those are kind of similar colors. And the z gets replaced by the k component here, which is also a z, coincidentally. So what this gives us is 2 cosine theta times 2 sine theta times z, multiplied by this thing we just found, which is the 2. So that 2 is, let's pick a different color. This 2 is this 2. That gets multiplied. That gets stuck with a dA. And then we look at r, and we say, oh, r is nice inequalities. 0 to 2 pi, 1 to 5. Now, because both of these are constant, it doesn't matter which one goes on the outside. So I listed theta first. I'll put theta on the outside. 0 to 2 pi, 1 to 5. Let me clean this up a bit. So I have an 8z cosine theta sine theta dz d theta. And then we just evaluate. And that's the result. So similar to before, we parameterize it with an r, we find the partials, we take the cross product, we take the magnitude, we turn the surface integral into a region integral. And just I want to make a point here that's sort of can be very helpful. It's very tempting to skip this step right here and jump straight from the step above it to the step below it. I strongly recommend not doing this. It's really easy to muck up your variables and lose track of things, and there are some really tragic consequences. So please try and make sure that you jump from here and then to here. It'll definitely be beneficial to not making mistakes, especially when we sort of get more complicated problems. It sort of gives you a breathing space. It's sort of like, okay, I converted it to an integral over r, and then I iterated it, and it breaks it up into pieces rather than trying to do everything all at once. So let me do yet another example. And again, I'm going to clear the screen so we have a nice empty space. Let me do this one. This one's not in the notes that are online, but I think it's, there are 2 more I want to do. The last one I'll do is in the online notes, but this one isn't. But I think it's better to do this one before the last one. So the description of sigma will be a bit confusing here, so we'll draw a picture to help clarify. This is the piece of, let's say, y equals 16 minus x squared. Now this is, I'm thinking about this as a as a parabolic sheet, so there's an implied z here, which can be anything. So this is in the first octant with x and y. Oh, sorry, let me undo that. Let's say with x and z bounded by, actually, sort of here's a slightly better way to say this. Let's say the first octant to the right of this little rectangle. Oh, this little triangle, sorry, get my rectangles and triangles confused. And what we're going to do is we're going to find the integral over sigma of, say, something nice, z ds. Now, first of all, the description of sigma is very confusing here. So let's draw a picture of sigma so we can understand what all this weird description is that's going on here. Right? So first of all, It's the piece of y equals 16 minus x squared. So 16 minus x squared, if it helps, let me draw that separately. 16 minus x squared, if you do that in the xy plane, goes like this. It's a parabola opening down. It's here at 4 and then negative 4. So I want the piece of, now when I move that rather into 3 dimensions, it becomes a parabolic sheet that wraps around this way. It's a bit out of sync. Let me clean that up a bit. So this is y equals 16 minus x squared. We're looking at the piece of that, which is in the first octant to the right of this little triangle that we drew. So this little triangle, I'm going to draw this in red down here. This is in the xz plane, the little triangle that's right here. Let me actually do this. Let me go back here, tidy this up a bit. Let me do this in red. This will help. So those little red triangles are the same red triangle. Goes out to 2 and 2 in both cases, 2 here, 2 here. And the surface we want, let's do this final surface in green, is the piece of the parabolic sheet which is to the right of this. So if we go to the right of that, we get what's like a, it's like a little triangular patch. So it's a patch of the parabolic sheet that's to the right of this in the first octant. The statement in the first octant isn't really necessary here. We could have just said to the right of the triangle. This is a confusing description. If I gave you something like this on an exam, I absolutely would clarify what's going on because it's very hard to interpret, but it makes for an interesting problem, which is why I want to do it. So this is the sigma that we're looking at. So take a second to make sure that you see that these red shapes are the same and that what we've got here, sigma, is the piece of the parabolic sheet that's in the first octant. Again, that bit's not really necessary. To the right of that red shape, right? So it's to the right of this right here. And that's our sigma down there. And we want to find this integral right here. So what we'll do is we'll parameterize sigma. And so what we see here is the red triangle is a really good description of x and z. Right? It gives us good, maybe inequalities we can come up with. And then we know what y is in terms of x. So what we can do is we can use x and z. We can do xi. Y is 16 minus x squared. And z is just z. And here we have to be careful. This is where x and z are restricted by, now let me draw these as a triangle again. And then I'm going to draw it as inequalities. So this is the R, if you like. This is a little triangle that extends to 2 units in each direction. Now, if I use inequalities for this, I cannot say that x and z both go from 0 to 2. That's a square. Right? This set of inequalities, I'm going to think about it as x going from 0 to 2, and z going from 0 to... So I'm thinking of this as a vertically simple region, and the line that's on the top here is the line z equals 2 minus x. So if this is a bit confusing, it's because this line right here, this is why it's helpful to label our axes, this is z equals 2 minus x. This bottom line is z equals 0. That describes that R. Here I drew it in black instead of in red. So those become the inequalities that bound the R. Right, so it's a bit different than before because these are not all constants, but that's okay. And then what we'll do is we'll take R sub x. This is 1i minus 2xj plus 0k take r sub z, which is 0i plus 0j. Sometimes these cross products work out really nice. Plus 1k, like really simple. Take the cross product. So for the I component, I get negative 2x times 1. That's negative 2x. For the j component, we get 1 times 1. So that's negative 1j. For the k component, we get 0. Take the magnitude. Square root of 4x squared plus 1. And then we take the integral that we're working with, integral over sigma of z ds. This becomes an integral over r. The z gets replaced by z by the k component, which is z. So again, there's sort of a sneaky none switch happening here in that this thing right here is replaced by this thing up here, which is the same thing. But I sort of have to track through it anyway just to make sure everything's good. And then we have our 4x squared plus 1 dA. And then what we do is we iterate it. Now, here we have to be careful. I have to put the x on the outside because it's the guy with the constants. And I have to put the z on the inside. I'm going to write something about that in a second. Fill in the integrand dz dx. So the last point I want to make, because from here we just integrate, is that this must be on the outside. Must be, let's say, x on outside, because x has constant bounds. Or maybe it would be better to look at it this way, is that must be z on the inside, because z does not have, or let's say it this way, because z has x's in its bounds. So that final point, we just go and we evaluate everything's a z and an x, and we're good to go. So this one is a little trickier for two reasons. One, the description was a bit more confusing, but once that makes sense, it's also a bit confusing because the region is not just inequalities with all numbers anymore. The inequalities in this case have, one of them has a variable in it. The same will happen in this last example we do, which will be even sort of maybe a little more confusing, maybe a little less confusing, depending on what you're comfortable with. So again, let me clear the screen, start from scratch, work through this example. All right, so last example. This is one that's in the notes. So let's find, let's let sigma be the part of z equals 7 minus x. That's a plane. Inside r equals 2 sine theta. And let's find the integral over sigma of x squared z ds. So we need to make sure that we understand what's going on here. R equals 2 sine theta. Right. As a surface, this is a cylinder. And z equals 7 minus x is a plane. Let me draw both of these. Now, the 2 sine theta, that guy by itself, as a circle, looks like this. This is one of our, this is in 2D. Oh, sorry, that's an x right there. We're going to extend that in the z direction. So that's going to be over here, extending up. The z equals 7 minus x, that hits up here at z equals 7. And as x gets bigger, z gets smaller. So as we come forward along the x-axis, it drops down, and then it sort of extends in the z direction. So what we've got here is this plane that cuts down through this thing, like this. And it's the piece, the sigma that we're interested in, is the piece of the plane that's inside the cylinder. So that's that thing in here. So it's not a circle because you've tilted this thing. So if you imagine like a sheet of paper slicing through a perfect cylinder will give you an ellipse. So sigma in here is an ellipse. You don't need to really understand that to do the problem, but it can help you visualize what's going on here. Right? So it's the piece of the plane that's inside the cylinder. So once that makes sense, same approach. We parameterize this. So then how do we do this? All right, so let's stop and think. Well, we know that x and y form this strange circle, like the circle that's offset above the x-axis. But x and y themselves are not good variables. But polar, like r and theta, might be a good choice here. Right? And we know that z is 7 minus x. So if we know what x is going to be, we know what z is. So we'll use r and theta. And so this might be the most confusing parameterization that we've done in this particular section. So we'll do r cosine theta I, and then r sine theta j, and then over here we have 7 minus x, but x is r cosine theta. And this is with, so in this case, what we're describing is the r's and thetas that give us this shape right here. So let me do r, let me draw a little red circle. Now, this r, we're thinking of it in an xy plane. But with r and theta, we would have theta between 0 and pi, and r between 0 and 2 sine theta. Now, just to be clear, the 2 is coming up right here. This goes out to 2, and this goes up to 2. Now, if that's a bit confusing, think about how we did double integrals. Well, if we were doing a double integral over this region, these will be our limits of integration. So this isn't as confusing as we might think. It's got an alpha and a beta, and a near function and a far function, or an inner function, outer function, however you want to think about it. Okay? So once that's established, and again, before I go further, just let me say, just clarify, this guy, this is our z equals 7 minus x, but x is this thing over here. So it's the 7 minus the x that we're using. So then what we do, take our partials. This is going to get awfully icky, but that's kind of fun. So I take the derivative with respect to r. So we get cosine theta I, because theta is the constant, plus sine theta j, plus, and this derivative with respect to r is negative cosine theta k. Then we do it with respect to theta. This is a little icky because we have some negatives that show up, and the r remains because that's a coefficient. So negative r sine theta I plus r cosine theta j, and then plus 0 minus, in this case, minus a minus because the derivative of cosine is negative sine. So plus r sine theta k. Then we take that cross product. So this is going to simplify a bit, but let me write it all out just so we can see. So if we hide the I components, I get r sine squared minus a minus r cosine squared. This is just the I. Then we do minus. Let me do them one over the other because otherwise they definitely won't fit. We hide the j's, we do the determinant. We get r sine cosine minus, so there are a bunch of minuses. There's minus, a minus times a minus, so minus a plus. So minus r sine theta cosine theta j. And then for the k, we hide the k's, and we get r cosine times cosine, so r cosine squared theta minus a minus r which is a plus r sine squared theta. So I commented on this earlier. These cross products very often simplify. They look terrible, but like this guy, when we simplify it, the I component just becomes r. The j component becomes 0. And the k component just becomes r. So when we take its magnitude, we get the square root of r squared plus r squared, really r squared plus 0 squared plus r squared, which is the square root of 2r squared, which we can simplify further to r root 2. Then, the integral that we're interested in, squared z ds. So again, we have a bunch of substitutions that go in. This becomes an integral over our r. The x, let me color things. Let's do the x here gets replaced. That's a terrible color. That's way too light. Let's say the x here gets replaced by the I component right here. And the z here gets replaced by the z component right here. So this x becomes r cosine theta, that's squared. The z becomes 7 minus r cosine theta. Then we put in this thing we just calculated, the r root 2, and then dA. And then we iterate this, and again, in this case, the theta has to be on the outside because the r has a variable and its bounds. So 0 to pi, 0 to 2 sine theta. This probably can be cleared up, but let's just leave it alone for now. R cosine theta squared, 7 minus r cosine theta, r root 2, dr d theta. And then that just gets evaluated. And I'm less interested as to whether you can trudge through these evaluations because these are things that are typically done in software. They're not done in by hand anymore. But it's all getting to this iterated integral that have to be done by hand. Right? That's the hard part. So that's the end of 15.5.